Welcome to this video lesson. In this video, we will be looking into how we can use third law of motion to solve elevator type questions. All right, we need to know that scales measure the normal force acting on them. So let's have an example here. We got a scale right here. I'm going to call it S for scale. Got surface A. On surface A, and we got a person right on it, and I'm going to call this P for person, and I am going to use purple to bring our person and make them the system, and let's draw a force diagram on them. For our person, we have a force of gravity acting on them, and that's from the earth acting on the person. And the only other contact that they have is with the surface of the scale, and there could be a frictional force or a normal force based on that contact. No frictional force, we're going to assume that the person is not going to be moving left or right, and that their weight is centered, so they don't have to move right and left. So the only other force is a normal force acting on them, and that's coming right from the scale because they are in contact with the scale. So this is a normal force from the scale onto the person. These two forces need to have the same magnitude in order to balance themselves, because the forces acting on this person are balanced, and the person is not accelerating up or down. We are now going to make the scale our system. So for this scale, there's going to be two forces acting on it. There's going to be a force from the person acting on it. There's going to be force of gravity, actually three forces, and there's also going to be a force acting from this surface A on it. So the force acting from the person on it, it has to be this same force here in terms of magnitude based on third law of motion. So I'm going to draw it about the same magnitude. This is the normal force acting from the person onto the scale. And then there's going to be a force of gravity also acting downwards. The scale is pretty light relative to the person, so that's going to be pretty small. And this is the gravitational force acting on it. This is on the scale, this one is on the person. And finally, there is going to be, we know that this is not moving anywhere. It's not accelerating up or down, and therefore there needs to be another force over here, and that's from the contact force from surface A onto my scale. So I'm going to draw this a little bit bigger. And this is a normal force from the surface onto the surface A onto the scale. Okay, so this definition says scales measure the normal force acting on them. There's two normal forces acting on this. One is coming from the surface and one is coming from the person. In this case, it is what the person is the force from the person onto the scale, and that's the normal force that is measuring. So in terms of magnitude, I'm just going to highlight this with red. This is the normal forces acting. It's actually not measuring this normal force over here. That's going to be a different value, but it's the normal force from the person onto the scale. And that force is also equivalent to this force in many situations. So these two forces are the same in terms of magnitude. So if I want to figure out what is the force acting or what is the reading on the scale, then I would have to find one of these two. So in normal circumstances, if I have a person standing on a scale, let's say this person has a mass of 20 kilograms, and they are standing on a scale. This is surface A, this is the scale, this is the person, and I want to figure out the reading of the scale. and I want to know it in units of Newton and units of kilogram. When I go up a little bit, I am going to draw a force diagram. Actually, just going back, we already have the force diagram right here, so we are going to use this. We can see that we can either use this or this. This one has a lot less forces on it. Well, not a lot, but this one has 2, this one has 3. And we also don't have any information about the mass of the scale, and we can't find the gravitational force acting on the scale, but we do have the gravitational force acting on the person because we have their mass. And therefore, let's use this force diagram. So using a force diagram of person, or use system being the person, we will use F net y is equal to sum of the forces. We have to take one of the sides to be positive, either up or down. I will take, in this case it's not accelerating, I will take up to be positive, it doesn't really make a difference. And the forces are going to be the force acting normal plus the force of gravity acting on the person, and that's going to equal to mass times acceleration. We know that the person is not actually moving up or down, so this acceleration value is going to equal to 0. I'm going to put the values in the next step. And in terms of the components, I'm going to turn everything into magnitudes. This is a vector. It's going up. My positive is up, so I'm going to turn it into a positive. This vector over here, the gravitational force acting on it is moving downwards. My up is positive, so they're opposite, so it's going to become negative when I turn it into a magnitude. And the gravitational force acting on the person is going to be the mass of the person multiplied by the gravitational acceleration acting on them. This is going to equal to mass times acceleration, but the acceleration in this case is 0 because my object is neither accelerating up or down, so this is going to be 0. I am going to rearrange this, and I will get, I'm going to add MP and G to both sides, or MP times G. I'm going to move up a little bit now, and FNSP is going to equal to 20 times 9.81. And this is going to have a reading of 196.2, which will be approximately 196 newtons. So this is the normal force acting from the scale onto the person, and since the scale reads the force normal from person onto the scale, and since that magnitude is equal to the normal force from scale to person, therefore this is also going to be 160 newtons, and that is my reading in units of Newton. Now there's many different types of scales, but the way many of them usually work or used to work is they would have certain springs, and you could actually find a displacement that is caused when somebody comes and stands on it, and that displacement is turned into a force. And that force is usually measured in Newton. And then what they do is they measure in Newton, which is a unit of force, and then they turn that into kilograms, which is a unit of mass. And they do this by dividing by 9.81. So basically, when you want to figure out what's the scale reading and you have it in Newton, all you have to do is you have to turn that into a mass by dividing it by 9.81. So here, scale reading will equal to 196.2 divided by 9.81, and that should give us 20 kilograms, which is what we had originally. That's the weight of the person if the object is not accelerating up or down. All right, we're going to look at another situation now, and that's usually when you stand in an elevator and you move up or down, and then you're going to feel different in terms of what your how you feel like in terms of your weight. So let's move up, and this time we have a person standing on an elevator and standing on a scale, and the scale is inside an elevator, and the elevator is accelerating upwards, let's say at 3 meters per second squared. And we want to figure out the mass of the person is actually let's say MP is equal to, let's say, 80 kilograms, and we want to see what is the scale reading in this case. I'm going to start off again by drawing a force diagram on the person. So I'm going to isolate the person. So system is person, or P. And in this case, the forces acting on the person, one is Fg, and that's coming from Earth, somewhere here. The elevator is going up, and the only other force acting on the person is the normal force acting from the scale, because it's directly in contact with the scale. It's not directly in contact with the elevator, just the scale acting upwards. But in terms of the magnitude of this force, you can see since the person is accelerating upwards, this force needs to be larger. So I'm going to draw this a little bit bigger, and this is going to be the normal force acting from the scale onto the person, and my object is accelerating upwards at a rate of 3 meters per second squared. Okay, I have the information. Let's figure out what the scale reading is, and we know that the scale reading can be found by the normal force acting from the scale onto the person. So I'm going to just say system P again, the person, and F net Y is going to equal to the sum of the forces. That's Fn SP plus Fg acting on the person, and that's equal to mass of the person times the acceleration. Note that whatever your system is, that needs to be the mass that you're using here. And in terms of directions, my acceleration, I'm assuming, oh, actually I know that it's going upwards, so I am going to put a positive here. Before solving this problem, just think about this situation. Whenever you're in an elevator and the elevator starts moving upwards, for a brief moment, once it's accelerating, you will feel either heavier or lighter. Which one is it? And think about it right now, and once we solve it, you can see what the force reading is and what mass that translates into, so you can see whether that makes sense or not in terms of how you have felt previously. All right, we're going to turn everything into magnitudes. I have a vector. I'm assuming up is positive, so this is going to be positive because it's also going up. My Fg, it's going downwards. My up is positive, so I'm going to use a negative. In terms of magnitude of force of gravity, that's mass of the person multiplied by the gravitational acceleration, or the magnitude of it anyways, and this is going to be mass of the person times the acceleration. And my acceleration is positive, and this is positive, so I can just use the magnitude of the acceleration. I'm going to use a little bit of math here just to show you something. I'm going to rearrange by adding this term to both sides, and that will become mass of the person times acceleration plus mass of the person times gravitation or magnitude of the gravitational acceleration. I can now factor out mp, and this will become ma plus g. Interesting. So now you can see that initially the mass of the person or the weight of the person is just mass times gravitational acceleration. When the object is accelerating upwards, we're adding acceleration to gravitational acceleration. So, sorry, the acceleration of the elevator to the gravitational acceleration, and this would mean that they're going to weigh a little bit more. Let's put in some values in here. We have 80, and my acceleration is 3, and this is 9.81. And putting this all into my calculator and getting the correct number of significant figures, I'll have 3 plus 9.81 and multiply that by 80 to get approximately 102. And we have two significant figures, so actually I'm getting it's about 1,000. So 1.0 times 10 to the 3 newtons. And if I want to translate that into kilograms, some mass reading is going to be, I'm going to use the exact value on my calculator divided by 9.81, and that's going to equal to approximately 100. It's 104 on my calculator, but it's going to be 100, and I need it to two significant figures, so 1.0 times 10 to the 2 kilograms. So it's kind of like, sometimes we call it the effective mass, so, or apparent mass. So when the person is standing on the elevator and accelerating upwards, they actually feel heavier. So instead of feeling about 80 kilograms of mass, they would feel about 100 kilograms of mass, which is significantly more. It's about 25% larger here. All right, let's now do one last example, and this time we are going to have a person on the elevator, and the elevator is going to move downwards instead of, or accelerate downwards instead of accelerating upward. Note that if the elevator is going at a constant velocity, things don't change because there is no acceleration and the forces are balanced. But in this case, let's say it's accelerating downwards at a rate of 3.0 meters per second squared instead. Let's have the same mass, 80 kilograms. And let's see how that would change. I should have started with 100. It's a lot easier to compare the values, but that's okay. We're going to do the same concept. We're going to take the person as the system. So system is going to be our person, and the forces acting on them is force of gravity acting on the person from Earth, and the force of normal acting from the scale onto the person. Okay, good. And let's write our second law of motion here. F net y is equal to the sum of forces, that's FNSP plus FGP. That's going to equal to mass of the person times their acceleration. I'll take, in this case, I know the acceleration is downwards, so I need to make sure that this force is bigger when I'm drawing the forces in order to do them properly. And my acceleration is this way at 3.0, just so that it's a little bit easier to see. I'll have it here. And since my acceleration is downward, I'll take down to be positive, and I'll plug everything in. So I have I'm changing everything into magnitudes now. So this force over here, it's going upwards. My down is positive, so this becomes negative. My gravitational force that's going down, this is down, this becomes positive. In terms of magnitude, the gravitational force is mass of person times gravitational, or the magnitude of gravitational acceleration, and that's going to be the mass of the person multiplied by acceleration. Acceleration is down, positive, and therefore I'm going to use a positive magnitude here. I'm going to rearrange this. The way I will do that, I'm trying to isolate for this, so I will add this to both sides and subtract this to both sides in one step, and I will get the magnitude of the force from the scale to person is going to equal to the mass of the person times the magnitude of gravitational acceleration minus the mass of the person times the acceleration of the elevator. I'm going to factor out MP, and I'm going to get G minus A this time instead of plus. Very cool. So note that last time when you were going up, you always feel a little bit heavier as you're accelerating upwards, and once you're going at a constant velocity, you don't feel that extra weight anymore. And when you're moving downwards, just when you start moving downwards, since you're accelerating, you will feel a lot lighter, and once you go at a constant velocity, you no longer feel that. And then when you're slowing down also, your acceleration changes upward, so you will feel lighter again when you're later on when you're slowing down as well. And that's why at the end some students especially like to jump, because you feel a little bit lighter and you'll have a little bit of a higher jump. Okay, mass of the person in this case is 80, gravitational acceleration 9.81, acceleration 3. I'm going to plug all of that on my calculator, and I will get 80 times 9.81 minus 3 brackets, and I will get 544.8, which is approximately 540 newtons. And that's kind of my force there. And therefore, scale reading in newtons will be Fn acting from the person onto the scale, which is same as the magnitude of the normal force acting from scale to person, which therefore is equal to approximately 540 newtons. In order to find it in kilograms, you divide 544.8 by 9.81, because that's what the scales do. And when you put that on the calculator and you use two significant figures, you will see that you will get approximately 55.5 or 56 kilograms. And putting this in the calculator, this is actually about 70% of 80 kilograms, so about 30% weight reduction when you're accelerating at a rate of 3 meters per second going in this direction. So when you're going down, acceleration is down, so you feel lighter. When you go and slow down, the acceleration goes back upward, so you will feel heavier. Same time when you're going up, initially when you accelerate upwards, you feel heavier, and when you're slowing down to get to your destination, you will have an acceleration going downwards, so that's when you usually do your jump and you feel like you can jump a lot higher. And that's the concept of elevators. There's more concept to this, especially when you're dealing with situations in which you have two-dimensional forces. But since in grade 11 in Ontario curriculum, we don't go in depth with two-dimensional forces, I am not going to cover that in this particular video. I hope the video was helpful in giving you some ideas about how elevator questions work, and have a wonderful day.